Hi everyone, and welcome to another digital design class. In the previous class, we spoke about fundamentals of digital systems, the benefits of using digital systems compared to analog systems, how we convert an analog signal to a digital signal, and how do we convert digital to analog. As you remember, from analog to digital, we call it the ADC, or analog to digital converter. We use sampling. And for digital to analog, we call it a DAC, or digital to analog converter. We simply bridge the gaps and connect the dots using a capacitor. Then we started with the binary digital system and how a binary digital signal works. We have different levels. If it's a binary, we have zeros and ones. 0 usually means it's 0 volts, and 1 usually means 3 volts or 5 volts, depending on our system. One thing that I wanted to add here as well is sometimes some systems, instead of having 0 and 1 and 0 being 0 volts, the logic of 0 is actually somehow a little bit above 0 volts. And the reason that we have that is because we want to differentiate between when the system has been grounded and when it's a logic of 0. Because sometimes you should simply have a short circuit and the output of a transistor would be grounded. Therefore, you're going to see 0 volts in the output. And to eliminate that error, in some cases, the logic of 0 is around 0.3 volts, something like that. And if it's 0, it's considered an error. We just discard that. Anyway, and I explained about the undefined region and why do we have undefined region. Do you remember why do we have this undefined region? The undefined region is for separating the 1 and 0 to have an area to reduce error. As I mentioned, sometimes when we go from 1 to 0 and 0 to 1, we have overshooting. And we want to have I would say, a safe area between 1 and 0 to be able to accurately determine if this is a logic of 1 or logic of 0. And I also spoke about different voltage levels. We can have 0 and 12 volts or 5 and 0 volts. And the higher we get, we need more power to be able to switch from the logic of 1 to 0 and 0 to 1. And the lower the voltage gets, we need less power. But if it gets too small, the difference between the logic of 0 and 1, we may have errors in our system. We started with the power of 2 and with decimal numbers and the number systems. We solved some problems on decimal numbers. We solved some problems on octal number systems, which is the base of 8. For the base of 8, the digits are between 0 and 7, which we have 8 digits. And the way that we find the number, it's going to be the summation of the digit times its weight. Let's solve another problem on octal number systems, and then we would go to binary systems. Please give me a number between a 2-digit number between 0 and 60, something like that. 52. Thank you. So we have 52 in a base of 8, and we want to convert this to the base of 10. So first digit would be multiplied by 8 in the power of 0. So it's going to be 2 times 8 in the power of 0. And the second digit is going to be 5 times 8 in the power of 1. And we add them together. So it's going to be 40 plus 2, which is going to be 42. So this would be 5, 2, and the base of 8 would be 42 or 42 and the base of 10. Okay. Let's solve another one. We want to convert, oh, let me make this a little more difficult. 3, 8 in the base of 8 is what in the base of 10? And the first person to solve this, I'll give them extra points, bonus points on their first homework. Does anyone have the answer? I'm sorry? 32? Okay. Who else has 32? Everyone else? Does everyone have 32? Yes. What do you have? 24. What do you? I'm sorry? 32. Okay, perfect. So 30 is wrong. 24 is wrong as well. We don't have a number as 38 in a base of 10. The digits can go only from 0 to 7. So you can't have a digit of 8. So 38 is a wrong number at the base of 8. Okay. When you want to write 8 decimal in the base of 8, we write it as 1, 0. So 3, 8 is incorrect when you have the base of 8. Okay. Now let's solve for another base. Let's do this. 2, 3 in the base of 4. What is this equal to in the base of 10? By the way, you're gonna have at least, usually it's 4 questions in your FE exam for visual design. And these exams, in the FE exams, one of the easiest topics to get good points on, easy points on, is digital design. That's the reason I will solve a lot of problems. So you can just, by just looking at the problem, you can determine. And sometimes they have trick questions like what I mentioned already, like 3, 8 in the base of 8, number that it doesn't exist, something like that. So 2, 3 in the base of 4, what is the answer? This is going to be 3 times 4 in the power of 0. This is 2 times 4 in the power of 1. Okay. Again, all of them, they have the same equation as the decimal, okay? We have this equation, which is the digit times the weight, which we start again from the fraction points, and we go to the left, and the first number on the left will be 0, 1, 2, 3, and so on. So the first number, this one is 0 and 1, so 4 in the power of 0, 4 in the power of 1. So 2 times 4 in the power of 1 would be 8. 3 times 4 in the power of 0, 4 in the power of 0 is 1, so it's going to be 3. So 8 plus 3 is 11. Yes.
What do we do in this situation where we have a number that doesn't fit the base, like 38?
It's unsolvable.
Okay.
You say it's a wrong number.
Oh.
It's like, converting a to a digit.
Gotcha.
And you can do that in a hexadecimal, okay? But you can't do it in base of 8, 10, and I'll explain what. In hexadecimal, we go 1, 2, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. A is 10, 11 is B, and so on. And I'll explain more about that. It's a little confusing, but You'll get used to it when you solve a lot of problems. So let's do another one. 4, 3.5 in the base of 5. We want to convert this to the base of 10. So this 0, 1, -1. So 5 in the power of -1, 5 in the power of 0, 5 in the power. Does anyone have the answer? So 4 times 5 in the power of 1 plus 3 times 5 in the power of 0 plus 5 times 5 in the power of -1. So this is going to be 20 plus 3 plus 5 times 1 over 5. Am I correct? What would this be? What if this was, let's say, let's solve another one. 5, 6.4. So what is wrong with the previous one that I had? I did a mistake in the previous one. It shouldn't be a 5. I wanted to see if you could. So the maximum that I could go is 4. That's the reason I didn't have a fraction part, and that's wrong. When you see that you're going from a fraction to one that doesn't have a fraction, then you know that something is wrong. You must have a fraction here. Okay? So it's 4 times 5 in the power of -1. So this would be 23. This would be 23.4 divided by 5 is going to be what? 0.8. Thank you so much. 23.8. Now let's solve this one. 56.4. Again, 43.5. And I wanted to show you in fraction as well. This is an incorrect number in the base of 5 because we have this 5, which cannot be, even if it's in the fraction. So 56.4 in the base of 8. It's going to be 5 times 8 in the power of 1 plus 6 times 8 in the power of 0 plus 4 times 8 in the power of -1. It's going to be 46.5. Am I correct? Yes? Okay. Do you want me to solve another one or you want me to go to the next? Another one? Yes, you move on?
Yeah.
Move on, okay. I've solved a couple of these as well. Let's go to a binary, and where is the binary? Oh. So for a binary number, I accidentally, I think, erased that. So for a binary number or for a base of 2, how many digits do we have? We would have 2 digits. What are our digits? 0 and 1. And the weight in a binary system would be equal to the base and the power of the position. And the magnitude, again, would be the sum of the digit times the weight. So now let's solve a problem. Imagine we have this number 1101 and it's the base of 2 and we want to convert it to the base of 10. So the position, this is 0, position 1, 2, 3. And then we multiply it by the digit itself. So this is going to be 1 times 2 in the power of 3 plus 1 times 2 in the power of 2 plus 0 times 2 in the power of 1 plus 1 times 2 in the power of 0. 2 in the power of 3, if you go back to this table, that's the reason I said this table is important, the powers of 2. What is 2 in the power of 3? 8. So 1 times 8 is going to be 8 plus 1 times 4 plus 0 times 2 plus 1 times 1. 2 in the power of 0 is 1. So it's going to be 8 plus 4 plus 1 gives us 13. So this would be 13 in the base of 10. Now, give me a random binary number. Someone give me a 10, 10, 10. 10, 10, 10, and give me a fraction. 3/5. It should be in binary. So let's say 1, 1. Okay. Again, because it's binary number, the digits can only be 0 and 1. By the way, when you read this, it's like 100. It's not 100. Sometimes you get confused. This is 100. Okay, 100 is actually equal to 2 in the power of 2, which is 2 in the power of 0, 1, and 2, which is 4. So now I have this binary number in the base of 2, and I want to convert it to the base of 10. I'll give you a few minutes to solve this, then I would solve it. And again, the first person to solve it is going to get extra points on their first homework. Did everyone solve it? What is the answer?
42.75.
Perfect, yes. So this is 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, 2 in the power of 3, 2 in the power of 4, 2 in the power of 5. This is 2 in the power of -1, 2 in the power of -2. So 2 and 1, I'm just going to calculate the ones that are 1. The ones that are 0, the weight is 0. The digit is 0. I'm just going to ignore it because it's going to be 0. So 1 times 2 in the power of 5 plus 1 times 2 in the power of 3 plus 1 times 2 in the power of 1 plus 1 times 2 in the power of -1 plus 1 times 2 in the power of -2. 2 in the power of 5 is 32. 2 in the power of 3 is 8. 2 in the power of 1 is 2. So 2 plus 8 plus 32 is going to be 42. And the fraction part is going to be 2 in the power of -1 is actually 1 over 2, which is 0.5. 2 in the power of -2 is 1 over 2 in the power of 2, which is 1 over 4, which is 0.25. So 0.5 plus 0.25 gives us 0.75. So it's 42.75. 42.75. Do you want me to solve another problem? Or you want me to move another one? Okay. Give me a random binary number. Let me continue with. Give me a random binary number.
1, 0, 1, 1, 0, 1.
Okay. Do you want to add the fraction or no? 0.11. Good. 0.011 or 11. Yeah, that's it. Okay. So we have this number in the base of 2. We want to convert to the base of 10. Again, I'll give you 4 minutes to solve this, and then I would stop solving. Has anyone solved it? 91? Okay. Good, perfect. So this is 2 in the power of 0, 2 in the power of 1, 2 in the power of 2, 2 in the power of 3, 2 in the power of 4, 2 in the power of 5, and 2 in the power of 6. So 1 times 2 in the power of 6 plus 1 times 2 in the power of 4, because 2 in the power of 5 is 0, plus 1 times 2 in the power of 3, plus 1 times 2 in the power of 1, plus 1 times 2 in the power of 0, plus 1 times 2 in the power of -2, plus 1 times 2 in the power of -3. 2 in the power of 6 is 64. 2 in the power of 4 is 16. 2 in the power of 3 is 8. 2 in the power of 1 is 2. 2 in the power of 0 is 1. So 16 plus 64 gives us 80, plus 10 is 90, so 91. And 2 in the power of -2 is 0.25. 2 in the power of -3 is 0.125. So it's going to be 91.375. Did you get this result? All of you? Thank you. Good job. Great job. Okay. One thing that I want to mention, then it's going to help you a lot. If I have a 3-digit number, this is a note that I'm going to give you, like 111. What is 111 equal to? I want to calculate 111. No. It's going to be equal to 7. 2 in the power of 0, which is 1, plus 2, plus 4. So 4 plus 2 plus 1 is going to be 7. How many digits do I have here? 3 digits, yes. What is 2 in the power of 3 equal to? 8, yes. So I have 3 digits here. These 3 digits can show between 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. How many digits do we have here? 1, 2, 3, 4, 5, 6, 7, 8. I have 8 digits. Yes. And what do the digits show? Between 0 and 7. So between 0 and 7, which is 8 digits. So 0, 0, 0, and I'm going to write the decimal number of these in front of them. So this is going to be 0, 1, 2, 3, 4, 5, 6, 7. How many digits do I have? 8 digits. Okay. So if I have a memory that it has 9 bits or 9 digits, 2 in the power of 9 is going to be equal to what? 512. Okay. So the numbers in this 9-digit binary numbers is going to be between 0 and 511, which totals 412 numbers. Okay. Let me give you another example. Imagine I have this number 1111111, and I want to convert this to a base of 10. If I only want to do it manually, it's going to take a lot of time. How many ones do I have? 1, 2, 3, or these are parentheses. I'm going to draw the parentheses with the different. So 1, 2, 3, 4, 5, 6, 7. Yes. 2 to the power of 7 is equal to what? Yes. So this number is, so the numbers are between 0 and 127. So if everything is 1, this would be 127. You can calculate it. It's going to give you 127. Now let's do something else. Can you calculate this for me? 1, 2, 3, 4, 5, 6, 7, 8. Oh no. 7 ones, and the last one is 0. What is this number in the base of 10? So how many digits do I have? 8. 2 to the power of 8 is equal to what? 256. Yes. So if everything was 1, this number would be what? And I'm missing the last one. So it's 254. This is going to help you a lot, especially when you are doing your FE exam. Now, let me show you another trick. If I have 3 ones, what is the number? 1, 1, 1 is equal to what? 7. Okay. What if I add a 4th digit and make everything 0? What is this digit? This is 8. Okay. So what is this number? 1, 2, 3, 4, 5, 6, 7. Two in the power of 0, 2 in the power of 1, 2 in the power of 2, 2 in the power of 3, 2 in the power of 4, 2 in the power of 5, 2 in the power of 6, 2 in the power of 7. 2 in the power of 7 is what? 0, 1, 2, 3, 4, 5, 6, 7. 2 in the power of 7 is equal to what? 128. So the number, this number is equal to 128. Okay. So now let's solve something else. Okay. Let me do it on the same page. Oh no, I don't have enough space. So now let's solve this. Or make it, yeah, 9. How many digits do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes. This is 3. This is 2 in the power of 9. 2 in the power of 9 is 512 plus 3. I have 515. 2 in the power of 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay. Is it clear? These are some examples that I solved last semester. I just checked them. For example, 110, if we want to convert it to decimal number, it's going to be equal to 6. 01101. And I actually checked this one. If I put a 0 before the 1, it's like putting a 0 before a number 9 on the left side of it. Does it make it a different number? No. Okay. So if I, isn't this equal to this? So 09 is equal to 9. So any number before on the left side, any 0, it's not counted. So 2 in the power of 0, 1, 2, 3, and 4. And when we calculate it, it's going to give us the same as if it was 110. And I solved 110. It's going to be 13. Another one, 111.11. It's going to give us 7.715. And we solve different. And I already mentioned about this, something like this. And it's the other way around. Imagine if everything was 1, but one of them was 0. Okay. If everything was 1, what would the answer be? I would solve this in a, let me teach you addition and I'll solve this. It's gonna be very easy. You just subtract it from that number. So let's continue with hexadecimal numbers and I'll get back to that particular question when I go through addition and subtraction. So we learned about decimal, octal, binary. Now another very important number system in a digital systems is the hexadecimal number. Hexadecimal is in the base of 16 and we have 16 digits. The numbers are between 0 and 15, which makes up 16 digits. So we obviously can show 0 to 9 with numbers, but we can't show 10, 11, 12, 30. That's the reason we show them with words. So it's going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Number 10 is shown with A. Number 11 is shown with B. Number 12 is C. 13 is D. 14 is E. And 15 is F. And I don't know if in programming, fundamental programming language, when you want to compile a code, you would see FF. That's the reason. So the computer only understands 0 and 1. Doesn't know what A means, B means, C means, none of that. Controlling computer is via controlling a bunch of switches. It's made out of transistors. It's the same thing with our brains as well. Our brain converts everything to electric signals going through our neurons. And if you actually think of it, a large language model like a LLM or these chatbot generative AI, those also, the servers are just seeing a bunch of zeros and ones. They don't see a picture, they don't see a word, they don't see a script, they just see zeros and ones. And through what we call different machine learning algorithms, I don't want to go through different techniques. One of them that they use for generative AI is what we call reinforced learning. It's basically like teaching a baby what a table is. You show it 10 different tables, and that's called a training process. And then you show the baby a different type of table and ask what this is. And that's the test or validation process. What does the kid do? Looks at the table, goes through the cornea and projects on retina. Retina has around 100 million different cells, which are called cones and rods. Some of them are just for detecting light, so they just can see in black and white. That's the reason in dark you just see in black and white. And the cones are just for colors, and we have 3 different one of them. We have the tall, medium, and short ones, which could detect red, green, and blue. It's exactly like a camera. That picture is then converted to electric signals carried to our brain, and our brain processes that. Through training, when we were a kid, we already know what a table looks like, what a chair looks like, and so on. So that gets into zeros and ones. But if we want to short that, make that shorter, we can use a hexadecimal, and I'll explain how that is done. So a hexadecimal is a very good way to be able to convert and send and compile code, and that's the reason we use hexadecimal. And the digits are, again, between 0 and F. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And for example, if I want to show the number 15 in hexadecimal and decimal, converted to decimal, I show it with F. F is equal to 15. Simply that. So F would be actually, and it's other things, everything else is exactly the same as what we had in a binary system or a octal system or a decimal system. Now, let's solve a couple of practice problems. Imagine I have this number 2b, and I want to convert this to a decimal number. So again, the first digit is going to be multiplied by 16 in the power of 0 because our base is 16, and it's the first digit. And the second digit would be 2 times 16 in the power of 1. So if I multiply this, 2 times 16 plus b, which what is b? It's 11. 11 times 16 in the power of 0, which is 1. So it's going to be 32 plus 11 gives us 43. Okay, 43. Now I want you to solve this. A, B, decimal. I want you to convert this hexadecimal to decimal number. Computers have Windows as well, or it's just Linux. Have you tried to sign in with your password?
Yeah, it's Windows.
Windows? Probably has. Do you have access to internet on there? Can you open Circuits Lab? Search Circuits Lab on it. Has anyone solved it? Circuits Lab? Yes. I want to see if there's a blue around. X. So. um, More you work with. But I see. And it's great, thank you. So we can use Circuits Lab without installing. So. What is the answer for this? Perfect. So A, B in a base of 16. A, B in the base of 16 is A is equal to 11 is B and A is 10. So 10 times 16 in the power of 1 plus 11 times 16 in the power of 0. So 160 plus 11 gives us 171. Now, what about this one? F 0.8 and the base of 16. What is it in the base of 10? Has anyone solved it? So I think f is equal to 15 times 16 plus 0 times 16 to the power 0, so 0. Plus 8 times 16 in the power of -1. So what is 15 times 16? Yes, perfect. And what is 8 over 16? 0.5. So it's 240.5. Thank you. Now that we learned hexadecimal numbers, do you want me to solve another one or that's fine? Okay. And please stop me again at any point if you have any questions. Now let's go through addition. Again, this is pretty easy, basic things that you learn in elementary school, probably. When we want to add a decimal number, for example, we want to add 55 to 55. We add 5 plus 5, and then we have a carry, which carries on to the next number. Again, 5 plus 5 is 10, plus 1 is 11, and so on. And we do the same thing when we add binary numbers. Let me go back to slideshow, current slide. I'll show you how. So as you know, that stopped working. Do any of you have Surface Pro? Surface. Do you have Microsoft Surface Pro? Any of you? Okay, never buy it. It's a piece of garbage. I always have problems. I think I have to restart my computer. Let's. Okay. So imagine now we want to add two binary numbers. We already learned about decimals. You're already familiar with that and how a carry works. Now let's add two binary numbers together. So first binary number, we have a 1, 1, 1, 1, 1, 0, 1 plus 1, 0, 1, 1, 1. So the only difference that we have here is when you add two ones together, 1 plus 1, what do we get in a binary number? 2. What is 2 in a binary number digit form and a base of 2? Perfect. When you add 1, 1, you don't get 2, you get 1, 0. What if you add 1 plus 1 plus 1? What do you get? You get 1, 1, which is equal to 3. Okay. Now, if I add 1, 1, this one, plus 1, it gives us 1, 0, or 2. I would put the 0 and move the carry on to the next. Now, again, 1 plus 0 plus 1 gives us what? What is 1 plus 0 plus 1? Yes, 1 plus 0 plus 1 is 2, which is 1, 0. So you're going to have the 0 and the carry on goes to the next. Now, what about 1 plus 1 plus 1? What is the answer? 1, 1, perfect. So 1, and then the other one goes carry. And then 1 plus 1 plus 0, it's 1, 0. So we're gonna move the 0, and the 1 goes to the next step. And 1 plus 1 plus 1, 1, 1. And the last one, 1 plus 1, 1, 0. Okay. Now, 1, 1, 1, 1, 0, 1, if we convert it to decimal, is equal to 61. And 1, 0, 1, 1, 1, when we convert it to decimal, is equal to 23. You can double check that as well at home. 61 plus 23 is equal to what? 84. And if you convert the 1 that we got, you would get 80. And again, this is the only way that the computer can process these numbers. It will convert it to binary, and it's a bunch of switches. And you can see that you can convert anything, do all the math that you want and the boarding and everything just by simply showing it in with 2 bits with a switch. 0 and 1, you can show anything. Now, binary subtraction. So for the binary subtraction, it's the same principle that we have for decimal subtraction. What happened when you wanted to, for example, subtract 0, 1 from 1, 0? So 1 is greater than 0. What did we do? We would borrow from the next one. And then we would have 1, 0 over here. 1, 0 is 2. Minus 1 gives us what? 1. And then I have 0 here. 0 minus 0 gives us 0. This is 2 minus 1 gives us 1. Okay. It's the same principle here. So 1, 1 minus 1. What is 1 minus 1? 0. So nothing here. What about 0 minus 1? I have to borrow from the next one. Yes. So this becomes 0. This becomes 1, 0. Or 2. You can write it as 1, 0 or 2. Now 2 minus 1 gives us what? Gives us 1. Again, we have 0 minus 1. 0 is less than 1. I can't subtract. I have to borrow from the next one. So it's going to be, again, 2 minus 1 gives us 1. Now 0 minus 0 is 0. Now I have this problem. 0 minus 1. I want to borrow from the next one on the left. Can I do that? No. Then I'm going to go to the next one. So that's going to be 2. And that, again, is going to be borrowed. It's going to be left with 1. And now I have 2 minus 1 is 1. 1 minus 0 is 1. And 0 minus 0 is 0. Now, if I convert these to decimal, it's going to be 77 minus 23 gives us 54, which if you solve the result and you convert that to decimal, you're going to get 54. Is it clear? Do you want me to give you some practice problems? Do you want me to solve some? So if you see this in your FE exam, the easier way to do it is that you're allowed to take your calculator, and all of these calculators do binary to decimal. You can simply just convert them quickly to decimal, subtract them, and find the result. Some of them even do, binary subtractions. But this is for you how to know, and they also do binary to decimal, decimal to hexadecimal, and so on. But I just want you to know that the principles of how this is done and how a computer does it. And later on, I will explain about half adders, full adders, and subtractors and how they work and the principle behind this. Now, what about binary multiplication? Binary multiplication is exactly like a decimal multiplication. How did we do a multiplication if you have several digits multiplied by several digits? We multiplied the first digit by the whole number, then we shifted 1 to left, multiply the second one, and so on. So if I do this, what is my first row of answer is gonna be? Perfect. 0, 0, 0, 0, 0. Because 0 times 1, 0, 1, 1, 1 gives us 0, 0, 0, 0. Now we shift one digit to the left. Now 1 times the digit, this gives us 1, 0, 1, 1, 1. Again, we would do another shift, 0, is gonna give us 0, 0, 0, 0, 0. And again, 1, again, one other shift gives us 1, 0, 1, 1, 1. Now, what do you have to do? Perfect, add them together. Well, now we're gonna find a summation. 0 plus nothing is gonna be 0, 0 plus 1 is gonna give us 1, 0 plus 1 plus 0 give us 1, 1 plus 1 gives us 1, 0, so we keep the 0 and add the carry on. Now 1 plus 1 again is gonna give us 0, 1, and now 1 plus 1 plus 1 gives us 1, 1, and then 1 plus 0 gives us 1, and the last one goes. Now, if you find the decimal numbers, again, you can convert easily from, you can see that the multiplication would have the same results that if you had a decimal numbers, you're going to have the same results. Now, you may ask, why did we learn octal and hexadecimal? And why didn't we learn base of 4 or 5 or 6? And why are they so important? There is a relation between octal, binary, and hexadecimal, and they could be directly converted to each other. But other forms of binary number systems, base systems, it's much difficult. You have to convert them first to decimal and again from decimal to any other. And so that's the reason octal, the base of 8, and especially hexadecimals are very important. So we can go from octal to decimal, from binary to decimal, and from hexadecimal to decimal, the way that I showed you, the weight times the digit and the position. And we can also go from decimal to octal, binary, and hexadecimal. But we can also directly go from binary to octal and from binary to hexadecimal. Now I'll explain how that is done in a bit. Now, before we do that, I just want to mention something else. In computer systems, you may have heard about byte, okay? And bit. Bit means one binary number. That could be either a 0 or a 1, okay? So it's a space for one binary. What is a byte? Yes, 8 of these bits gives you 1 byte. So you're going to have 8 bits will give you 1 byte. So usually we measure everything in bytes because it's easier, more efficient, and we never say this memory is 6 megabits. It's always megabytes. And 6 megabytes, it's actually 6 times 8. It's going to be 48 megabits, okay? But this is just for you to know. Now, how can we go from decimal to octal and binary and so on? Let's go from decimal first to binary and do a decimal to binary conversion. I think we only have maybe time for one of them today and solve some examples. And then we would do decimal to octal and hexadecimal, leave it for next week. So we already learned how to go from a binary number to decimal. But how do we go from a decimal number to a binary? So the first thing we do, we would divide that number by 2. We will divide it by the base that we want to go to. Here we want to go to the base of 2 or binary, we divide it by 2. If we wanted to go to base of 8 or octal, we would divide it by 8. So in this example, we have a number 13 in decimal. First, then we will divide it by 2. So 13 divided by 2, the quotient would give us 6. What is the remainder? 1. And what is the coefficient? It's gonna be the remainder, which is 1. Now, I would keep the quotient and I would divide it again by 2. So as mentioned, we would divide the number by the base of 2. We take the remainder, either 0 or 1 as a coefficient, and take the quotient and repeat the division. So again, 6 divided by 2 gives us 3. What is the remainder? 0. 0 is going to be our coefficient. Again, we would divide the quotient for 3 by 2. The quotient would be 1, and the remainder would be what? 1. And we would keep it as our coefficient. And again, we will keep the last quotient as well. You can just keep this and, skip that, but 1 divided by 2, this is 0, and the remainder is going to be obviously 1. Now we would read the number from A3 to A2, A1, A0, so from bottom to top. And that's going to be our answer. So 1, 3 is going to be 1, 1, 0, 1. Now, let's do a practice problem. I want you to convert let's see, 31 to base of 2. So I want you to convert the decimal number 31 to the binary number. And again, the first person to get the results gets extra points on their exam. On their, I'm sorry, homework. Has anyone solved it? What is the answer?
1, 1, 1, 1.
5 ones?
Yes, sir.
Yes, perfect. So 31 divided by 2, it's 15, and what is the remainder? 1. 15 divided by 2, it's 7, and what is the remainder? 7 divided by 2, 3, perfect, and 1. Still 3 is greater than 2. Again, 3 divided by 2, 1, and then 1. And you can say 1 divided by 2, 0, and 1. And you just write it like this, going 1, 1, 1, 1, 1, which gives us 31. But there's an easier way to solve this. Do you remember the table that I showed you, powers of 2? What is the closest number to 31? What is 32 equal to? 2 in the power of what? 5. When we have 2 in the power of 5, what are the numbers? They are between 0 and 31. So they are between 0, 0, 0, 0, 0, and 1, 1, 1, 1, 1. So 1 gives us what? 31. And let's go back to the one that I already showed you. So this is a good example. That, for example, if I have 1,000 and let's say I have 510, okay? What is the closest number to 510? 512. What is 512? 2 to the power of 9. So 2 to the power means it's between 0 and 511. Am I correct? So if everything is 1, I have 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. Then what would this be? This would be equal to 511. If I subtract 1, meaning the last one is 0, I get what? 510. Okay, and this is a good way to solve it when you are doing an FE exam or something. I can give you the other examples in your homework. Now, do you want me to solve another problem, or do you want me to go to the
division something?
Yes, and I'll explain that after this. But I have to first explain about fractions first. Sorry, just give me 1 second. I thought it's showing there. So I didn't realize that it stopped showing on the. So 31 divided by 2 is 15, and then 7, 3, 1, and the answer is 1, 1. And did you see the other one that I wrote, or you didn't see it on? So my other example was 510, as I mentioned. The closest number is 512, which is 2 to the power of 9. So the numbers are between 0 and 511. So you're gonna have 1, 2, 3, 4, 5, 6, 7, and 1, 0. So this gives us 510 if the last one is 0. Now, what if we have a fraction? We want to convert a decimal fraction to a binary conversion. Example is 0.625. It's a decimal number, and we want to convert it to base of 2. What we do here, for the previous one, we divided it by 2. This one we will multiply by 2. So 0.0625 multiplied by 2 gives us 1.25. What we do is we ignore the integer. Actually, by integer, ignoring, I mean that we don't multiply it again by 2. And we keep that integer as a coefficient, okay? In the previous one, we kept the remainder as the coefficient. So here, we would keep that as our coefficient, and then we will multiply the fraction again by 2. So the fraction is 0.25, we multiply by 2, we get 0.5. Now, we will continue this until the result is the fraction part is completely 0. So again, we will keep the integer part, is going to be our coefficient. We will multiply the fraction again by 2, and now the fraction is 0, so we would end it at this point. And again, we will keep the integer and we use it as a coefficient. So the answer would be 101. Now, let's solve a practice problem. I want you to convert 28.375 to a binary number. So 28.375 to a binary number. Has anyone solved it? Yes, I'll give you a few minutes. Okay, let's solve it. So 28 divided by 2, it's 14, and the remainder is what? 0. Am I correct? 14 divided by 2, 7, 0. 7 divided by 2, 3, 1. 3 divided by 2, 1, 1. And 1 divided by 2. So it's going to be 1, 1, 1, 0, 0. And for the fraction part, 0.375 multiplied by 2. What does it give us? 0.750. Am I correct? 0.750. So I would keep this as a coefficient. Multiplied by 2 is 1.5. Again, I'm going to keep this as my coefficient. And then 0.5 multiplied by 2 gives us 1.0. So it's going to be 1, 1, 1, 0, 0, 0, 1, 1. Which is equal to 28.30. Did you all get the same result? Okay, perfect. Okay, I think it's enough for today. I will post the first set of homeworks this weekend, and you're gonna have 1 week to complete it. Please let me know if you have any questions. Again, our lab would start at the third or fourth week when we reach a certain point, which are the logic gates. Okay. Thank you so much and have a great weekend.